Hello. Thank you very much. Thank you. I confess I've never had an introduction like this before. I will never have one again, I'm sure, but and make the most of it while it happens. So thank you very much, and thank you to the organizers of Science and Cocktails for inviting me. This is a great opportunity to talk to a very sophisticated audience about science and about why I love the ocean and why I'm worried about its future, but why I'm also optimistic about its future. So what I want you to do is to relax and take in some of this art. This is a painting by Winslow Homer, and he's an American artist. When he exhibited this, it was considered to be too dark and too miserable a subject because there was no hope. And so after exhibiting it, he took it back to his studio and he painted the boat in the distance. And that gave hope to the viewer. Maybe this guy will be saved. Maybe he has a chance. And I think the way that we feel probably about the present and about our position at the present time is perhaps a little bit like the man in the boat. We worry about the future a lot. We're not sure how it's going to end up. We hope we will be saved. And of course, unlike this sailor who has no chance of saving himself, we have to be the architects of a better future ourselves. So let me see. So the world is a very wet planet, and this is how most of us think of it, as 7/10 sea and 3/10 land. But in reality, it is even saltier than that. And if we look at it from the other side, then the world looks almost completely ocean. This is just a huge area of ocean. And that on its own is not quite the whole story, because when you take into account that third dimension of depth, then 97% of the volume of living space on Earth is made up by ocean, which is incredible. It means that rather than the world, the land world, which is our fiefdom, where we have been and where our attention is focused, that is not the only thing. In fact, it's a minor part of the world when it comes to the space available for creatures to live in. So consider for a moment one drop of ocean water. Inside this perfectly clear drop of water, there are many, many microbes. In fact, the world was microbial for billions of years, and it only became multicellular after a very long period of time. And those 200,000 viruses in that drop, if you multiply that one drop to the size of an ocean, then the viruses make an incredible force. They're equivalent to the weight of 175 million blue whales, or 70 times the weight of all the people on planet Earth. But there's one fact which is even more surprising about viruses in the sea, and that is that if you put them all end to end and stretch them out into outer space, I ask this sometimes to audiences, how far do you think they would go? Go on, shout out Mars. Alpha Centauri, not even there. No, they would go 10,000 light years. No, 10 million light years. 10 million, I'm getting it wrong. 10 million light years, it's incredible. You know, that is just an almost unimaginable distance into space. And what it tells you is that viruses are incredibly numerous, and they're also quite long and thin. So while we're on the subject of the small creatures in the ocean, the phytoplankton, the plants, the drifting plants that live in the open water, those phytoplankton have played a huge role in making planet Earth habitable and producing the oxygen that we're breathing. And this is a really wonderful animation which shows 6 years of phytoplankton coming and going with the seasons as the seasons pass, and you see the productivity moving in response to where the winter ice is forming, and it's moving backwards and forwards. And you can see great features of ocean circulation on here. The squirt of green across the middle of the Pacific Ocean, that's the equatorial upwelling. That is the place where nutrients are brought from deep down, and they fertilize the surface waters, and they produce this streak of green. You can also see, if you look at the north coast of South America, you can see where the Amazon River exits into the Atlantic Ocean. And this is this great squiggle of productivity. The Orinoco is north of that too. So this is an incredible image of how the ocean is working, how it's like the breathing in and breathing out. This is the planet breathing in and breathing out. And it's a totally beautiful and mesmerizing thing to look at. It's also incredibly important to us because ocean productivity is extremely important for the thing that we see so much of in Denmark, seafood. Seafood is everywhere here, and you have a great love of ocean life served up on a plate. It's beautiful, and I've been enjoying it for the last day or so with my wife, who's come with me to Copenhagen. But there are many people who absolutely depend on the ocean for the animal protein that they need. And more than that, there are even a bigger number of people who depend on ocean life for the essential nutrients in their diet. And without that sea life, they would be malnourished. And so the ocean is extremely important for feeding us. And it has been for almost all of modern human history. The earliest signs of seafood dinners that we know of come from 164,000 years ago in a cave in South Africa. And there's the remains of shellfish meals that were eaten then. But, one of the things that has become very apparent in the last 100 years or so is that the game is changing in the ocean, and that is because of our increasing planetary dominance. People are becoming a force of planetary change. There was a time when we feared the ocean, where the ocean had control over us, and we were humble in its presence. Of course, we still are in many cases, and the wildness of the ocean is still palpable, but we are now agents of change with the capacity to change the oceans too. And we're confronting two fallacies that we have held dear in our hearts for a very long time, one of which is that the sea will provide for us whatever we want, and then the second fallacy is it will take away whatever we don't want. And as the little introductory video shows, that's not a good solution. You can't just throw it away and expect a whale not to come back and bite. And that's what is happening. So our attitudes and our thinking to the ocean have changed dramatically in the last 50 years or so. And after World War II, we looked to the ocean as the solution to feeding an ever more densely populated planet. It hasn't turned out quite that way. In fact, seafood production has fed a growing population and has continued to, but only at the expense of overfishing many of the species that we formerly were able to catch in abundance. Now they're not nearly so abundant anymore, and we see marine life being depleted by continued exploitation. And you see scenes like this where we're treating what is an incredibly valuable resource as a cheap bulk commodity. This is something that we can endlessly take from the sea in industrial quantities. One fact, unfortunately, it's embarrassing for Denmark perhaps, but it is always shocking, is that in past times, you burned sand eels in power stations, because by adding sand eels to the fuel mix, you got a more efficient combustion. And that's just incredible that we would burn fish in power stations. And we would treat them as a resource that is so plentiful, you could never see the end of it. And of course, the end result of that is that now we see the oceans with far less wildlife in them than they had in the past. And only in the past couple of weeks, the WWF Living Planet report has reported that of all the monitored populations of wildlife, abundance has declined by 69% since 1970. And in the ocean, these declines are true as well. And in fact, for some of the biggest and most iconic life, the losses are even greater. We have seen much bigger declines, sometimes 99% in terms of the abundance of them. So that's one of the big changes that's taken place in the sea. It's being reversed in some places. Better management is coming in, so it's something that we have control over if we find the political will to do it. Another place where we need to find political will is in global change. And of course, it's now undeniable that the world is changing if you believe for even a second in science, because science says that in so many different ways that we are changing the planet with greenhouse gas emissions, and every year it gets hotter. And we can see that especially clearly when you look at ocean heat. So this is a time series of ocean heat content. And as you can see, almost every year is a record-breaking year in terms of ocean heat content. And that's good for us, because what it means is that we're being spared much worse things happening to us on land. The ocean is a huge air conditioner for the planet. By taking up all that extra heat that's being trapped by greenhouse gas emissions, well, it's done us a favor. And how big a favor? It's absorbed something like 93% of the additional heat that has been added to the atmosphere by trapping under greenhouse gases. And I ask this question too to people: how much do you think the atmosphere would have warmed if it hadn't been for the ocean taking up all of this extra heat? How many degrees centigrade do you think it would be warmer than it is today? The world has warmed a little over 1 degree centigrade so far. So without the ocean, how much would it have warmed, do you think? 10. I'm hearing a few 10s out there. Well, actually, yeah, it's a few 10s taken together, 36 degrees centigrade. So it would be Death Valley temperatures out there right now. And, that's even too hot for a chilly autumn day in Denmark. So we have been spared the worst effects of our greenhouse gas emissions. It's hard to visualize, how do you visualize how much heat that is? And, you can talk about numbers of, bazillion joules or whatever the biggest units you can think of are of heat going into the sea. But one very vivid way of visualizing how much heat is being trapped every day on Earth is through this particular study, which converted it into Hiroshima-sized bomb equivalents. And you might ask, how, from 1871 until 1990, or thereabouts, ocean heating was equivalent to the explosion of 1.5 Hiroshima-sized bombs per, now what is the time step? Seconds. This is what's great about coming to an audience of scientists. They know their stuff. And it's per second. Per second. How much heat is that per day? That's over 250,000 now. When we look at this recent part of the time series, 3 bombs per second is over 250,000 exploded per day. That's the amount of extra heat being trapped in the ocean. Now, because water has a huge specific heat capacity, it has not converted into a very steep rise in temperature as yet, but we can see the effects all around us. The temperature rise in the ocean is about 0.7 degrees Celsius above the historical period. But that's enough to have done a great deal of mischief underwater. And one way in which you can see this extra energy is in more powerful currents. Faster currents are flowing around the sea now than they were 150 years ago. Across 3/4 of the world ocean surface, we're seeing this kind of acceleration of ocean currents. And thinking about that, one of the things you don't think it's possible to change on that kind of scale is the planetary environment, but it's happening. And that's also expressed in the power of waves. So if you're an ocean-going sailor and you sail around the world, what you do is you shoot south down the Atlantic, if you start in the Atlantic, and then you get the winds to blow you around Antarctica, and then you come home. And you can do that faster now than you used to do. But it's a more dangerous trip because the seas are much bigger and more energetic and more powerful. And another way in which that heat is manifested in the ocean is in sea level rise. And here we see a century-plus time series of sea level rise, and you can see that we started zero in 1900. And the background to this is that since 7,000 years ago, when the sea stopped rising after the end of the last ice age, it has been more or less the same level. Unless, of course, you're bouncing back after the ice melted and the land is rising or the land is sinking. Those isostatic adjustments are important to relative sea level rise in places. But this is the eustatic sea level rise. This is the volume of the ocean. And the volume of the ocean is increasing because we're melting the ice, and we are increasing the volume that the sea occupies by warming it. Warm substances take up more space than cold. And in recent years, we've been measuring this very precisely using satellite telemetry and looking at the height of the ocean. And we can see that the sea is rising fast and has risen something like 20 centimeters in the last century. But when you look at that on a mapped scale around the ocean, the rise is not uniform. Some places have experienced much faster rates of sea level rise than others have. And if you see a piece on the news about the problem of sea level rise, then one of the places that they're likely to go is right here in the Western Pacific Ocean to an island nation called Kiribati. And they have been experiencing sea level rise of a rate of about 1 centimeter per year, which is just incredible speed. But that's the speed we'll all be experiencing by the end of the 21st century. And this is what's happening in Kiribati right now. They are seeing the tides overrunning the islands. And that's very bad news. It's not just inconvenient for a while the tide comes and goes, but it's killing all their crops. They have no possibility of growing crops when the seawater comes in and contaminates the soil. And it's not just Kiribati that's affected. Rich countries are being affected too. And this is downtown Miami Beach, another of those king tides. King tides are exceptionally high spring tides, and they happen a few times a year. And this illustrates one of those phenomena, and that is that extremes increase faster than averages. So, as the average rises over time, the extremes around those averages get bigger. And so we're experiencing more extreme weather, more extreme conditions. And here's another measurement that's been made of the ocean, that the biggest waves are getting bigger faster than the average size waves. Again, a reason to fear going around the world on a small boat, but a reason to hope that you could get around faster if you were lucky enough to not be capsized. Of course, that also leads us into the problem of cyclonic storms around the planet. And cyclonic storms have been gaining energy, and they've also, as we've started to see, they start moving more slowly, and they're expending that energy more slowly. And if any of you who've been in a cyclonic storm the last thing you want is for it to move slowly. You want that thing to go through like a train. But now they're sort of hanging around, and these poor people stuck underneath, being destroyed by cyclonic storms. If any of you are rich enough to contemplate buying yourself a second home somewhere in the tropics, you might want to consult this map first of the location of all the cyclonic storms that we have measured, and see that there is this band in the middle where you don't get cyclonic storms forming. And that's because it's not far enough from the equator for the Coriolis spin to spin up a cyclonic storm. You have to get a bit farther away from the equator for that spin that is imparted because we're on a rotating planet to kind of get those storms really going and sustain them. And it's the heat in the ocean that sustains them as they move over the sea. And the warmer the ocean is, the more energy goes into the storm, and the longer it will last, the higher the latitudes that it will reach. And the aftermath of those storms is truly horrible. It's devastating for communities. At the moment, we're in denial, so we tend to rebuild in exactly the same places that we were destroyed. But that's not a long-term sustainable option. We really need to start thinking about relocating as part of a package of adaptation to climate change. Looking at this scene of devastation, I always think to myself, who was that builder? You know, I bet his phone was ringing off the hook after the storm had gone through. Now, this is one of the rubbish photos in my talk, and that's because it's one of my own collection. This is me when I was a student back in the 1980s, and I was studying coral reefs. And I want to turn now to coral reefs, which have to be my favorite of all ecosystems, and they are extraordinary and incredible and vibrant and full of life, and any other kind of superlative that you want to add, it's worthy of those superlatives. A coral reef is one of the most beautiful places underwater. We've all seen them on television. If you watch Blue Planet 2, there was plenty of footage of coral reefs. You can't get enough of them. And for somebody who takes better photographs than me, this is a photograph by my friend Alex Mustard. And Alex won the European Wildlife Photographer of the Year some years ago, and he managed to impart artistry into his underwater photographs, and even if I can say it, kind of convey something of the beauty of the originals. And this is in Sharm el-Sheikh, Egypt, and you can see the contrast between the almost lifeless land surface, which has hardly any water, and the vibrant coral reef, which is thriving in the sea beneath. And coral reefs are geologically resilient ecosystems. They have built these geological structures that can be seen from space that last for thousands, tens of thousands of years. And it's all built by these little creatures that form colonies. Each of these little rings is a single individual, and they form a colony of individuals that live and grow together. And the greeny color of this coral gives away its secret and why it has been so successful biologically. And that is because inside the tissues of the coral, there is a plant. And that plant lives in a symbiotic relationship with the coral, and it gives the coral most of its food. So something like 90% of the food that a coral eats is produced by the plants inside it. Now, the plants get something in return. They get protection. They get carbon dioxide from the coral's respiration, which they convert into oxygen, which the coral likes. And so everybody's happy. They get nutrients as well from the corals. And this has turbocharged coral growth. So that is why we're in this geological period of extensive coral growth all over the world. And to give you an idea of what I mean, this is the edge of a reef in the Red Sea, and you can see all of these corals growing up towards the surface like plants, but also animals and also stone. And so their stony skeletons, the calcium carbonate that they're made of, forms this incredible resilient ecosystem. And they are places which just throng with life. And, for a place with few nutrients, the water overlying coral reefs is generally low in nutrients. And so the question of how do coral reefs have so much life in such nutrient-poor seas? It's like the oasis in the desert. And the secret to that is very efficient recycling and capture of nutrients. All the mouths you see in this picture capture plankton coming across the reef, and then they recycle it into the reef, and the reef thrives. And the creatures that live there are just fantastic. These beautiful harlequin filefish, they are exquisite, and they almost seem to get even more exquisite the more you focus in on the little details of these animals. And then there are these batfish, just extraordinary shape that they have, living, just hanging beneath this table coral head here. And sometimes the sheer abundance of life is breathtaking on reefs. And here is a school of snappers which have arrived at a reef in southern Egypt ready to spawn. And they have come from all over, some of them from hundreds of kilometers away, and they're ready to spawn in this great churning fury of fish, reproducing the next generation. Coral reefs are extraordinary from the perspective of what they do for us. So they protect coasts. And wherever you have a coral reef fringing a coast, you have protection for that coast. And you can see these waves breaking on the outside part of this coral reef. And by the time they get to the crest of the reef, which it sticks out of the water at low tide, then the waves moving into the calm lagoon. And so those calm lagoons are always thought of as being places of tranquility. And that's why we love to go to places like the Maldives for holidays and float on our backs in the calm lagoons. Well, for the Maldives, everything that is there is really a product of coral reefs. The islands are built on platforms of limestone that have been constructed by corals over thousands and tens of thousands of years. And those reefs, the living reefs, surround those islands, and they protect the people who live there. And they supply the islands with the raw materials, the coral rubble and sand that build them, and then they get stabilized by vegetation. And of course, sometimes the people almost overwhelm the space in those. And in the case of Male, the capital city of the Maldives, you can see they've now added the defense of seawalls around the edge of this reef. But will it be enough to keep the Maldives in business over the long term? And the reason that we're worried for the Maldives' future is because corals are very flaky in the face of a small amount of ocean heating. So this relationship between the coral and the plant is incredibly temperature dependent. And when temperatures rise a degree or more above the normal maximum, then the relationship breaks down. It's like when you go into the sauna with your husband or wife, you start arguing, and it breaks up. And so the corals have to get rid of these seaweeds that are in their tissues, and if they don't do that, they die. The problem is that if they do that, they die. And there's a little window in between where they can potentially, if the temperatures come down fast enough, they can regain the algae, the seaweed in the tissues, and recover. But if the temperatures remain high for more than about 8 weeks, then the corals starve to death and they die en masse. And what we've seen in the past couple of decades is episodes of mass coral bleaching and mortality that have rocked the world. The one in 1998, that was a huge event which took science by surprise. We had no idea this was going to happen. There had been a smaller bleaching event which had affected the Eastern Pacific, but this was a huge thing, and it was wrapped all around the planet. The Caribbean was affected, the Indian Ocean, the Pacific Ocean, and progressively these events have chipped away at the vigor of coral reefs. And so what we see now is a picture of falling coral cover and increasing fragility and vulnerability. And the Intergovernmental Panel on Climate Change has predicted that if we keep to the Paris Agreement, the most ambitious target of the Paris Agreement, keeping the temperatures less than 1.5 degrees centigrade above the historic average, the pre-industrial average, then we're still going to lose 70 to 90% of corals. 2 degrees centigrade of warming, and it's curtains for corals as we see it at the moment. And this is some data that we've collected in the Maldives. One of my students has been working on this as part of a project funded by Deutsche Bank, and you can see how that 97-98 bleaching event caused the collapse of coral. 90%, 9 out of 10 corals died during that event. And then they were recovering. They were struggling back, and they were looking quite good up to 2015. And then, boom, it happens again, and they're on their knees again, and they have to start recovering again. Here's another example. This is me when I was younger and less porky. And you can see I'm busy looking at the reefs in Bonaire in the Caribbean. And this is an island which has absolutely beautiful coral reefs. And my wife and I were lucky enough to go back there this summer and do exactly the same science again, survey the reefs, take the pulse, and figure out how well they were doing. And, the reefs when we were there in 1994 were not pristine by any means. They had recently suffered mass coral mortality for a different reason. They had been infected by something called white band disease, and white band disease impacted the 2 big branching species of coral that were very dominant in shallow water on these reefs and wiped out about 99% of them. Now, Ebola, if untreated, will kill 65-70% of people. So this is an incredibly lethal disease for corals, and it was devastating. And it turns out 15 years later, we discovered that the organism responsible for this is a human gut bacterium. So, we're used to thinking about diseases jumping from wildlife to us, but we caused a disease that jumped from us to coral. So what did it do? I mean, it wasn't just this. This is how coral cover has changed in the Caribbean over that period. And what we can see is that coral has just about halved in its abundance over that 28-year period. It's still there, it's still beautiful, it's still among the best places in the Caribbean, but it's suffered very badly over time. And then if you look at all the other bits of this, then you can see that the bad seaweeds, the fleshy ones that compete with corals for space, there's more of those now than there was in 1994. The good seaweeds, the ones that condition the reef and glue it together and provide settlement space for corals, there's less of those than there were in 1994. So, if I was a doctor looking at a human patient and I saw these vital signs, your blood sugar is too high, you're unfit, you need to lose weight, you need to change your lifestyle. But, of course, the lifestyle that corals need to change is not in their power, it's in our power. We need to change their lifestyle. So that begs the question of where are we headed now? I mean, where is the world going with all these kinds of changes? And to figure that out, we need to understand something called climate sensitivity. And climate sensitivity is the relationship between the amount of emitted greenhouse gases and the eventual rise in temperature that the world experiences. Now, at the moment, the science that we know of tells us that things will be okay if we keep the world to within 1.5 to 2 degrees of temperature rise. And you can see we are now getting perilously close to that. And as time goes on, you can see those bands getting closer and closer to the 1.5 degrees of rise over in the left panel. The right-hand panel is the amount of Arctic sea ice. So we're dangerously close already. We've got about 420 parts per million of carbon dioxide in the atmosphere. How much will that drive up temperatures? Well, let's think about the past as proxy for the present. And I wonder how many of you know much about the Pliocene. Well, the Pliocene was a few million years ago, 5 to 2.5 million years ago. And in the middle of that, there was a warm period which had similar levels of carbon dioxide in the atmosphere to the levels that we have now. In fact, just a little bit higher, about 450 parts per million of carbon dioxide. And temperatures were 2 to 3 degrees centigrade higher. Now, what would be the effect of raising the planetary thermometer by 2 to 3 degrees centigrade? Well, let's see. During that time, there were forests near to the South Pole. There wasn't much ice in Antarctica at that time. Greenland was ice-free. You can have holidays in Greenland, maybe even set up some recliners on the beach in Greenland. But this is the problem, that all of that ice had to go somewhere, and the answer was the ocean. And so we had sea levels that were 22 meters higher. This concert hall would be underwater in this kind of world. So, what can we do about this? And people throw up their hands and they say, I'm so depressed, there's nothing we can do about it, this problem is bigger than all of us. But it's not. We are moving in the right direction gradually, and gradually we're making the transition to renewable energy. And emissions reductions absolutely are of frontline importance in changing the outcome for us. And you can see that from this study. If you look at the date line in the top left hand of this slide, you can see us running through towards the early 24th century, 23rd century. There we go. We're running through the 22nd century and into the 23rd century. And this is the business as usual scenario. This is if we don't do anything. And you can see that the nearest analog temperature of one of these areas, now this is not the ocean, but think of the ocean as following along, is the Pliocene if it goes this yellow color, and the Eocene if it goes this orange color. There's a lot of the world that by the end of that time series is Eocene temperatures. And for those who are not familiar with that, there was open water at the North Pole, and it was 20 degrees centigrade in temperature. This was a much warmer world. Now, it wasn't uninhabitable. The mammals loved it. This is the rise of mammals time. But it's a scary world for us. Now, if you reduce emissions, if you get to a much reduced emission scenario, this is not the best case that the IPCC models. It's the kind of mid-range case. And what you can see is that reducing emissions enough to produce this outcome makes a big difference to the habitability of the world. And we're seeing temperatures that are still within the historical time range, or in the mid-Holocene, or in the last interglacial 125,000 years ago, when there was a warm period and sea level was about 6 meters higher than it is now. So emissions reduction is the first and foremost thing that we have to do, but we have to be kinder to the planet as well. And that means we have to change the relationship that we've got. We've got a bit of a toxic relationship with the sea and with the world, land or sea. And we've been used to taking what we need and using nature for our own ends. And now we have to transition to a much lighter touch. And that means doing things in a way that promotes the survival of nature. And as I say here, we have to prepare for the worst as well. And we have to now start thinking about whatever technological solutions we can for some ecosystems like coral reefs. And I work with an organization called the Maldives Coral Institute. It was founded by President Mohammed Nasheed, the former president of the Maldives and now Speaker of the House there in Parliament. And he founded this organization with a determination that he wasn't going to give up on the country just because this was a tough problem. And we are working to try and find ways of giving the reefs of the Maldives a better outlook for the future, and the people of the Maldives a better hope for the future. They don't want to become climate refugees, and one way that we can try and avoid that is by trying to future-proof corals, and that means using all the tools that are at our disposal to try and work with coral, work with biology to improve their resilience to rising temperatures and their ability to survive tough times and then to come back from them afterwards. And when it comes to the protection of the planet, we're also moving in the right direction. For the best part of the last 20 years, we've been pursuing targets for land and sea protection, of protecting 17% of the land and 10% of the sea. And we've realized that it's not enough, that more is necessary. And in December this year, the world nations will come together in Canada to devise new targets for planetary protection, not just the sea, but the land as well. And on the table for agreement is the idea of protecting 30% of land and sea, and protecting it well enough that nature can thrive in those places. And the idea is really catching on. The science says that we need at least 30% protected, and we also need to put in place high-quality protection. It's no use just creating a line on a map and saying this is a protected area and then doing nothing or carrying on with business as usual. We have to actually get to grips with giving nature the kind of protection from damaging and harmful human activities that impact upon their lives, so that they are able to genuinely reproduce more, grow more, rebuild habitats, and thrive even in the face of global change. Of course, that's not going to protect them from global change, but it will give nature a better chance, and therefore it will give us a better chance of having good lives in the future if nature is on our side and helping in the battle against climate change. So that's a very short introduction to some of the changes that are taking place in the ocean. And I've left a lot out. There's all kinds of other changes, other world shaping changes underway in the sea, which we haven't talked about. And if you want to ask me anything about those, then please ask questions. If you want the long answer about what I think will happen to coral reefs and am I optimistic for the future, then I wrote this book which tells about my experience of starting as a student in the 1980s and then seeing and living through all of this planetary change and trying to make sense of it and trying to do something about it to provide a world which is fit for our children and their children after them. So, thank you very much.